Okay, good morning, good afternoon, good evening, good night, depending on when you're watching the video. In this video, we are going to be working through exercise 1 from lecture set number 9, which is given on slide 15. This exercise will illustrate how to construct a confidence interval and perform a hypothesis test about two population means. So in this illustration, we have the following data. This data comes from, well, I'll just read the problem. So it says several neurosurgeons want to determine whether a dynamic system, which we can call the Z-plate system, reduced the number of acute post-operative days spent in hospital relative to a static system. Okay. Now, in the table, we have the number of days that set numbers of patients spent in the hospital after being either on the static system or the dynamic system. So the variable, the value that we're measuring in this case is the number of days spent in hospital after surgery. So that's what these values represent. Okay. So you can see for the dynamic system, there are a total of 14 patients that were evaluated. Okay, so for example, the first patient spent 7 days in the hospital after surgery. The second patient spent 5 days in the hospital. The third patient spent 8 days in the hospital. The fourth patient spent 8 days in the hospital, etc. So we have 14 different patients that were evaluated on this system. We are given X bar, so the average number of days these 14 patients spent in hospital post-surgery, and the standard deviation of these 14 values. Okay. The static system, we have the same variable. It's just from a different population this time. So this is the number of, we have 6 patients here, and this is the number of days these 6 patients spent in hospital post-surgery. So you can see that the average number of days here is 10.5, which is bigger than the average number of days for the dynamic system. And the standard deviation here is 4.59, which is also much larger than the standard deviation associated with the dynamic system. Okay, so in part A, given this information, it says, suppose that all assumptions hold. Is there sufficient evidence to suggest that the mean number of acute post-operative days in hospital is smaller with the dynamic system than with the static system at the 5% significance level? So this question is hopefully somewhat familiar. This is still a hypothesis test, but the difference here is that we are now comparing the mean from one population to the mean from the other. So we are asking a question about two population means. And the question we are asking is there evidence that the mean number of post-operative days is smaller? So this is very important. Okay. With the dynamic system than with static system. Okay, so we are asking, is there evidence at the 5% significance level that the mean number of days spent in hospital on the dynamic system is smaller than the mean number of days spent in hospital on the static system? Okay, so we're going to formulate a hypothesis test to answer this question. And we have to keep in mind that in this situation, we are comparing two means. So this is going to change the formula that are used within the hypothesis test. The structure of the test is going to be exactly the same. So we have we have an assumption check. We're actually told that those are all okay, but we'll go through it anyways. We have an assumption check, and then we have our 6 steps of the hypothesis test. But it's going to be a different set of formula particularly on step 3, and I guess a different set of hypotheses, step 1, compared to the one sample test we were studying before, because we're comparing two means now. So we have to be able to identify that the question is asking us to compare two means and not just and is not just asking us a question about one mean individually. All right, so we'll work through this. Okay, so part A. Okay, so the first thing that we do is check the assumptions. When we're checking the assumptions, we can do it in terms of each population separately to try and organize the information that we have. Right, so we'll have our assumptions for population 1, and we'll have our assumptions for population 2. Right? Now, for each population, it's actually the same set of assumptions that we studied in the one sample case. Right, so for example, the first assumption for each population will be that we have simple random samples, or just that the samples are representative. So they were collected in some random way such that we can consider them representative samples. We're actually told in the question that we can assume all of the assumptions have been validated. So these are going to get checked off. Okay. Now in part 2, or the second assumption rather, this is going to be the normality of X bar. Okay. And again, we can check these off because we're told that all assumptions are in check, but we'll revisit this in part C of this exercise. Okay, and then the third assumption, which isn't really an assumption, but I write it in the assumption check just so that we can organize our information, is that sigma is known. So in this case, actually in all three cases, it would be sigma 1 is known. And then for the normalities, it would be normality of X bar 1, normality of X bar 2, because we have two different populations. And then here we would have sigma 2 known. But in this case, we can check each of these off. We're given sample information, we're not given population information. So when the question says that all assumptions have been validated, that's referring to the simple random sample and the normality assumption. Again, the population standard deviation being known, or the population variance being known, isn't really an assumption of the test, but I like to write it in this section because now I know that I'm going to be using a t-test because I haven't checked these off. All right. So now we can start the hypothesis test. Okay. All right, so just like with the one sample tests, our null hypothesis will always be equality between the two populations. So we're going to have H naught mu1 equals mu2. So we're operating under the assumption that the mean of each population is the same. So in this particular example, we would be working under the assumption that the mean of each population, or the mean number of post-operative days for the dynamic population and the static population, are the same value. And that's what this represents. So the null is saying equality between two means. Okay. Now for the alternative, because we are comparing two values, we can actually write the alternative in either direction. So let's say we take it exactly as it's written. So we're going to write mu1 less than mu2. And then we have to just make sure that we know that mu1 is dynamic mean, mu2 is static mean. Okay. So as long as we know we have declared which population is population 1 and which population is population 2, that will inform the direction of the test. So here, I'm going to let the dynamic population be mu1, so I can write this as a lower tail test. If I let the dynamic population be mu2, this would just become an upper tail test. And that's perfectly fine. They're going to answer the same question. It really just depends on which mean we consider to be the first one and which mean we consider to be the second one. And this will influence the computation of the test statistic as well, because the test statistic is written as x bar 1 minus x bar 2. So if mu1 is the dynamic population, then x bar 1 has to be the sample mean for the dynamic sample. All right, so we'll run this as a lower tail test because mu1 is going to represent the mean for the dynamic population and mu2 the mean of the static population. Okay. All right, so on step 2, we will compute, or we will simply state our significance level, which is the 5% significance level in this illustration. Okay, so now on step 3, we're going to compute our test statistic. So because we're running a two-tailed test, the test statistic here is going to be x bar 1 minus x bar 2 minus mu1 minus mu2 divided by the square root S1 squared over N1 plus S2 squared over N2. And when we're performing these calculations, we just want to make sure that we do everything in the correct order. So for clarity here, we would do each of these fractions first, and then we would add, and then we would take the square root. All right, so all we have to do now is start to just plug in our values. Most of this is pretty straightforward because we have been told what x bar 1 is equal to. We have been told what s is equal to. We know the sample sizes because we can count how many observations are in each of the samples. So for example, x bar 1 is going to be 7.36. X bar 2 is going to be 10.50. Right. Now, what about this mu1 minus mu2? Mu1 minus mu2 is going to reflect what the difference is equal to based on the null hypothesis. Okay, in the null hypothesis, we have h naught mu1 is equal to mu2. Well, let's think about this. We could also write, given that this is an equality, this is the same thing as mu1 minus mu2 equals 0. Okay, so these two hypotheses here, they are actually the exact same hypothesis. It's just written in a slightly different way. In the black coloring, I have them written as an equality comparing one another. In the red coloring, I have them written as a difference such that I can see the null hypothesis is stating that mu1 minus mu2 equals 0. Now, this second illustration, the way that it's written in red, this is actually an expression that allows us to see that mu1 minus mu2 in the test statistic, this is just going to be written as 0. Okay, so here we have 0 in place of mu1 minus mu2 because that's what the null hypothesis is telling us the difference is equal to. All right, and now we can just continue to fill out our formula here. Right, so we're going to have 1.22 squared divided by 14 because we had 14 observations for this dynamic system plus 4.59 squared divided by 6. because we had 6 observations for the static system. Okay, okay, so now if we work this thing out, what we should get is negative 3.143. So that's the difference between mu1 and or x bar 1 and x bar 2 minus 0. So that's just 7.36 minus 10.50. And then this is going to be divided by 1.903. So that means that our test statistic here is negative 1.65. So that's the test statistic for this hypothesis test. Okay, now we have to determine if this test statistic is giving us evidence for or against the null hypothesis. So there are 2 ways that we can do that. We can take the critical value approach, or we can take the p-value approach. Now, we've seen lots of examples of this, and this is going to, even in the context of this test, the way that we perform this step does not change. So this is still going to be the same processes that we studied in the 1 sample case. The only difference here is that the degree of freedom calculation is more complicated for a 2 sample test. So the first thing that we're going to do before we actually look at the critical value and the p-value approach is to compute the degree of freedom. So the degree of freedom here is going to be S1 over N1 plus S2 over N2 all squared. I'm just going to make sure I have it correct here. So we're going to have S1 squared over N1 all squared, no, plus S2 squared over N2 all squared. Okay, and this is going to be divided by 1 over N1 minus 1, S1 squared over N1 squared plus 1 over N2 minus 1, S2 squared over N2 all squared. Okay. So for our 2 sample hypothesis test, this is how we compute the degree of freedom. And this will be the same formula that we would use for a confidence interval as well. And in part B of this example, I will go through that through a confidence interval construction, but we won't have to redo this calculation because it's going to be the same value because it's coming from the same data set. All right, so we have to fill this out and evaluate it. Now, the trickiest part of this is simply making sure that we do the right order of operations. So I've tried to bracket this accordingly such that we can see how we would perform the calculation. So we're going to want to do those 2 fractions separately first, add together, and then square that whole thing. And then on the bottom, we're going to have this. And then similarly, we'll just want to make sure that we do these 2 parts first and then add, and then we can put the whole thing together. So in this case, what we should end up with is 13.12 121 divided by 2.474, and that gives us 5.30. Okay, so this is going to be the degrees of freedom for this particular procedure. So now we can start our critical value and t-value and p-value approaches, and we know what degree of freedom to use. Okay? Now, momentarily, I'll discuss how we use this in the context of the t-table. We just have to round down as per the previous instructions, right? So here we're going to say use 5 degrees of freedom. And we always round down with degree of freedom. So even if this value is 5.87, we would still use 5. Okay, so we always round down with our degree of freedom. And now we can start the critical value and p-value approaches. And these will work in the same way that we saw before with our one sample tests. Okay, so this is going to be my sketch of a t-curve centered at 0 here. Right. I want to find, so I'm going to have df is equal to 5, and we have alpha 0.05. Okay, we're running a lower tail test in this case, so I'm going to have a negative t-value on 0.05 and 5. So now what I'm going to do is go to my student t-table, or to the student t-table. I have 5 degrees of freedom, 0.05. That gives me 2.015. So the critical value for this procedure is negative 2.015 because we are working in the lower tail. And then our test statistic was negative 1.65. Okay, so if our critical value is negative 2.015, it's a lower tail test. That means the rejection region is located here. I'll just slide this over so that it lines up a bit better. Like that. Okay, so our rejection region is in the lower tail. Our test statistic is negative 1.65. So that means our test statistic is going to be located, say, over here, for example. So this is t equals negative 1.65. And you can see that the test statistic does not get into the rejection region in this case. So we would have no evidence to reject the null. Right now, if we take the p-value approach, and just as a reminder, you don't have to do both, right? You can do one of the p-value or the critical value approach. So this is going to be my student t curve. I'm centered at 0 now. In this situation, I'm going to mark down where the test statistic is located. And so in this case, you can see that the p-value for this test is going to be the area below t is negative 1.65. So I'm going to have here the p-value is equal to the probability t is less than negative 1.65. Now, as we have discussed before, since the probability that t is less than negative 1.65 is the same thing as the probability that t exceeds positive 1.65. Okay. So these two things are equivalent. The lower tail area and the upper tail area are equivalent because of the symmetry of the curve. So if we go to our t-table, we have 5 degrees of freedom. Now we're going to scroll across the table and we're looking for 1.65. And you can see that this is actually right at the start. So 1.65 is in between 1.476 and 2.015. So that means the area of interest is between 0.10 and 0.05. Right, so here we would say, since the probability that t is less than negative 1.65 is equal to the probability that t is greater than 1.65, and 0.05 is less than the probability that t exceeds 1.65 is less than 0.1, then 0.05 is less than the p-value is less than 0.1. Right? So this is going to be the p-value for this particular test. And you can see, well, we'll go through it now in step 5. Okay, so if we use the critical value approach, we would simply say, do not reject H0 since test statistic is not in rejection region. And if we take the p-value approach, we would say, do not reject H0 since the p-value is greater than alpha. Right, and you can see, so our alpha in this question is 0.05. The p-value is between 0.05 and 0.1. So the p-value is a number that is bigger than 0.05 based off of our calculation. So therefore, the p-value must be bigger than alpha because alpha is 0.05. Right? So we do not reject based on either approach. Again, you don't have to use both approaches. They will give the same results. I just illustrate both so that you have them. Okay. All right, now on step 6, we would say at the 5% significance level. Okay, so we do not reject the null, so the data do not provide. That is consistent. The data do not provide sufficient evidence to suggest that the mean number of days spent in hospital post-operation is smaller with the dynamic system compared to the static system. Okay. So the same as we had with the one sample test, in our conclusion, we have 3 different components. We have the statement of the significance level, whether the data provide or do not provide evidence. So they do not provide evidence here because we do not reject the null. And then we are effectively just describing the alternative hypothesis. So there's no evidence that the mean number of days spent in hospital on the dynamic system is less than that of the static system. All right. So that is an illustration of a 2-sample hypothesis test. In part B, we are asked to construct a 95% confidence interval for the difference between the average number of days spent in hospital between the 2 systems. So this is going to be a three-step procedure like we had before. Now, the assumptions of this procedure are exactly the same as the assumptions of the two sample hypothesis tests. Okay, so this is going to be, we can just say C part A here, because we went through these assumptions in part A. So now we can start construction of the CI. So on step 1, we're going to write alpha, or sorry, we're going to say, well, yeah, actually we would say alpha is equal to 1 minus 0.95, which is 0.05. Okay, so the same computations we had in the one sample case. The confidence interval on step 1 is identical to what we had in the one sample case, at least in terms of finding alpha. Okay, and our degree of freedom is going to be 5.304. Right? So this is the same calculation we had in part A. So C part A again. Okay, so we're going to use 5 degrees of freedom, right? So again, we always round down with our degree of freedom calculation. So now we're going to have T alpha over 2 df. This is going to be T 0.05 over 2 comma 5. So this is T 0.025 comma 5. So if we go to our student T table, we have T 0.025 and 5. So now our critical value is 2.571. Okay. All right. So now on step 2, we are going to have x bar 1 minus x bar 2. Okay, we can put these in brackets to make it a little clearer. Plus or minus T 0.025 comma 5 multiplied by the square root S1 squared over N1 plus S2 squared over N2. So you can see that a lot of this, or most of these calculations, are exactly the same as what we had in the previous illustration. It's just the organization of the different components. So for example, we're going to have 7.36 minus 10.50 plus or minus 2.571 multiplied by the square root, and then we're going to have 1.22 squared over 14 plus 4.59 squared over 6. So that's negative 3.14 plus or minus 2.571 times 1.903. So that's negative 3.14 plus or minus 4.893. Okay, and then we add and subtract this. We have negative 8.033 to 1.753. Right. And then all we have left to do is conclude. So we can say we are 95% confident that the difference between the mean number of days spent in hospital post operation, between the mean number of days spent in hospital post operation when comparing the dynamic and static systems is between negative 8.033 and 1.753 days. Okay. So I have here, we are 95% confident that the difference between the mean number of days spent in hospital post-operation when comparing the dynamic and static systems is between negative 8.033 and 1.753 days. So again, this is the confidence interval is actually just telling us where we believe that difference exists. So this is an interval for mu1 minus mu2. So we are being told where we believe the difference or the value of mu1 minus mu2 exists. Okay, the last part of this is an evaluation of two normal probability plots. So this is more of a refresher. We've looked at lots of examples of this in the past, but here it says, consider the normal probability plots for the dynamic and static systems given on slide 16. Comment on the normality assumption for the inferential procedures used in A and B. So in parts A and B, we made the assumption that both we were told to assume that everything was checked off. So we assumed that the dynamic population or that the number of post-operative days for the dynamic population was normally distributed. And we assume that the number of post-operative days for the static system was normally distributed. And then we operated under that assumption. Okay, so now what we're being asked to do is go back and take a look using a normal probability plot to see if that was reasonable. When we're checking the assumptions for a two-sample test or for an independent two-sample test, we look at the probability plots for each population or for each sample separately. So we have one for the dynamic and one for the static. We're looking for the usual, so we just want to see if there's evidence that the points follow the line relatively well. If we look at the dynamic system, we can see that we have a lot of clusters of points. So a lot of the observations have the same number, or a lot of patients spent the same amount of time in hospital. For example, we have 7 people that spent 7 days in hospital. And then for the static system, we only have 6 points. Now, with the dynamic system, it actually looks pretty symmetric about the line. So despite the clustering, it does kind of seem like those points are, there is sort of a linear trend with those points. You'll notice that we have outliers 2 and 9 in this plot, and they're outside the bands. So that might imply that the tails are a bit heavier for this distribution than we originally thought. So if we wanted to be very strict, we would likely say that this plot is giving evidence that the tails are heavier than what we would expect for a normal distribution. So this would probably violate the assumption. Now for the static system, you can see there's 2 outliers identified, 1 and 2. They're still within the bands. But what we are seeing with this particular plot is a little bit of right skewness. And you can tell because the shape here is a little bit more of a curve than we would probably want to see. So again, if we're being very strict, we might say that we're getting a bit of curvature due to those 2 outlying points, and that might imply a bit of right skewness. So again, here we might be, if we're being very strict, would be inclined to say that this assumption is probably violated. Okay, so in each of these cases, we would probably say no evidence of normality, distributions, tails are too heavy. Okay, so those two outlying points, numbers 2 and 9, because they are symmetric about the line, but they're pushed outside the bands, that's implying that the tails are heavier than that of a normal distribution. So maybe something that's T-shaped. And then for the static system, we would say no evidence of normality distribution may be right skewed. Okay, so because we have that curved shape. All right, so in this illustration, we saw an example of a hypothesis test for 2 independent samples, an example of a confidence interval for construction for 2 independent samples. The test and the interval, they run using the same steps. So hypothesis test, I always teach as a 6-step process. Interval, I always teach as a 3-step process. Both start with an assumption check. The independent 2-sample tests are a bit trickier or a bit longer to run, mainly because of the degree of freedom calculation that's associated with step 4. So you can see that we have this long calculation for the degree of freedom in the case of 2 independent samples. So that really takes up a little bit more time in working that number out. And because of all the different components, we have to be very careful when we're putting this together. Whenever we compute degree of freedom, we always round down. The same way that I taught when you have a degree of freedom value that's in between 2 numbers on the table, you always round down. Okay, so this is consistent, always round down with degree of freedom. Otherwise, the hypothesis test works in the exact same way. Keep in mind that the null hypotheses we will usually work with will be mu1 minus mu2 equals 0. So most often the test statistic will have a 0 in the spot of mu1 and mu2. Right? And then we finished off with just a bit of a review of normal probability plots. As always, if you have any questions, please let me know.